Hello and welcome to this presentation of the embedded flash memory, which is included in all products of the STM32H5 microcontroller series. This table summarizes the features of the flash memory existing in STM32H5. Depending on the product, the flash size can be up to 2 MB. It also embeds a one-time programming area of 2 KB. The flash read data bus width is 128-bit. STM32H5 always supports a dual bank architecture. The swap bank option in the user option bytes is used to swap bank 1 and bank 2 addresses. As the non-volatile memory is divided into two independent banks, the embedded flash memory interface supports a read in one bank while a write or an erase is executed in the other bank. The sector size, which provides the minimum erase granularity, is 8 KB. Flash memory may be reconfigured for increased endurance of up to 100 kilocycles on the last 8 sectors of each bank. It also supports a read prefetch unit that increases the efficiency of Cortex-M33 CAHB bus. Finally, STM32H5 implements a product state lifecycle scheme, including support for regression and debug of closed device upon correct authentication. Each program erase operation can degrade the flash memory cell. After an accumulation of program erase cycles, memory cells can become non-functional, causing memory errors. Endurance is an estimated maximum number of erase programming sequences that the flash memory can support without affecting its reliability. Up to 8 sectors per bank may be reconfigured for an increased endurance of 100 kilocycles that can be used for data storage that usually needs more intensive cycling capability than code storage. These e-data sectors store less data to make up for the necessary redundancy for error correction. Data in flash memory are 137 bits wide. 9 bits are added per each quad word of 128 bits. The ECC mechanism supports 1-bit error detection and correction and 2-bit error detection. When one error is detected and corrected, the ECC correction flag is set in the flash ECC register. An interrupt can be generated. When 2 errors are detected, the ECC detection flag is set in the flash ECC register. In this case, an NMI is generated. The address and bank number at which the error has been detected are captured in status registers for further investigation. In case of error in the 16-bit word in e-data and OTP sections, it's possible to also examine the uncorrected data in dedicated register. To correctly read data from the flash memory, the number of wait states must be correctly programmed according to the frequency of the CPU clock and the internal voltage range. The table shows the correspondence between wait states and CPU clock frequency. Programming delay is also needed for higher clock speed, but regardless of core voltage. The Cortex-M33 fetches instructions and literal pool constants over the C-bus and through the instruction cache if it's enabled. The prefetch block increases the efficiency of C-bus accesses when the instruction cache is enabled by reducing the cache refill latency. Prefetch is efficient in the case of sequential code. Prefetch in the flash memory allows the next sequential instruction line to be read from the flash memory while the current instruction line is being filled in instruction cache and executed by the CPU. Prefetch is enabled by setting the PRFTEN bit in the flash access control register. It must be set only if at least one wait state is needed to access the flash memory. Note that prefetch tends to increase the code execution performance at the cost of extra flash memory accesses reaching over 4 core mark point per megahertz. As core mark code is entirely in iCache, meaning no cache miss after the first iteration, the prefetch has no impact on the core mark score when iCache is enabled. Power efficiency is better when prefetch is enabled. Read, program, and erase operations are supported in all voltage ranges. When trust zone is enabled, the programming and arrays must also respect the isolation boundaries. Arrays can be performed either with a sector granularity or for one bank or both banks. In the latter case, this is called a mass arrays. The ECC code is calculated and added to the data so that 137 bits are actually programmed. The contents of the flash memory currently being modified are not guaranteed if a reset occurs during a flash memory program or erase operation. The status of the flash memory can be recovered from the flash operation status register when a system reset occurs during a flash memory program or erase operation. It's the software's responsibility to check the flash memory status and to take corrective actions accordingly. The figure shows a simplified scheme of product state progression. Grey arrows represent increasing protection during manufacturing or development, while orange arrows represent ways of regressing to a previous state upon successful authorization. The process of assigning the authorization keys, as well as the extent of permitted regression, is called provisioning. It's also possible to exit the cycle of progression and regression permanently by assigning locked state. Progressing to more closed state is the normal product lifecycle that doesn't require security measures. Transition in direction to open state is a regression controlled by the debug authentication control. If debug unlock policy is set to locked, no regression is accepted. Tools are provided to facilitate the provisioning, integrate it with secure firmware install scheme, and distribute certificates allowing selected developers to establish temporary debug sessions. The regression and debug rights may also be delegated. Secure Hide Protection, or HDP, is controlled by Temporal Isolation Level, or TIL, used for ARM Platform Security Architecture, or PSA. 3 levels are available to facilitate secure boot process stages isolation. Each level increase blocks access to the lower levels, which only become available again on next reboot. Same mechanism works on smaller scale in dedicated key storage mechanism called the OBK. The area associated with TIL1, which is blocked by incrementing to level 2, is configured using option bytes. The threshold between TIL2 and TIL3 is a volatile setting in flash register called the HDP extension. If the two banks are swapped, the protection defined to physical bank 1 remains on the physical bank 1 unaffected by swapping. With exception of the STM32H5 the trust zone isolation is available on the STM32H5 series. When trust zone security is active, a part of the flash memory can be protected against non-secure read and write accesses. Deactivation of trust zone is only possible in the open product state or by orderly regression. Up to 2 different non-volatile secure areas can be defined by option bytes and can be read or written only by a secure access. 1 area per bank with a sector granularity. Watermark secure areas are complemented by bitmap-based definition, allowing for non-continuous secure areas. In each security domain, the privilege level of each flash sector is programmable, either unprivileged or privileged, by means of dedicated registers. 4 quadrants of isolated worlds are thus obtained: secure privilege, secure non-privilege, non-secure privilege, and non-secure non-privilege. Isolation may also be applied on the sectors of the high cycle area. Option byte key storage, or OBK, is a mechanism dedicated to storage of small data with high protection requirements, mostly cryptographic keys. The keys stored in this area are protected not only by the TIL, but also encrypted using epoch counter in the initialization vector. The epoch counters are incremented on each regression, making it impossible to recover the OBK contents after regression was made. New provisioning or installation of keys must be made. Secure keys placed in OBK sectors and protected by 9 bits of ECC. In case of tamper, all keys are read as zeros. The OBK uses two dedicated flash sectors. One is used as working, while the other stages the modifications. When the contents update is completed, they switch places. The keys stored may serve purposes of attestation, encryption, authentication, secure storage, or storage of important hash values. In addition to this presentation, you can refer to the following presentations: Security Enhanced Key Storage, STM32H5 Security Lifecycle, and STM32H5 Security Enhanced Anti-Tamper.